Hello everyone, I'm Frank and welcome to Learn How to Sudoku, where we take a very easy variant Sudoku puzzle and we break it down in detail so that you can learn how to Sudoku. Today's very easy puzzle is called Growing a Bonsai Tree by Jonesy. And here are the rules. Hello. Buongiorno. I think I already used that before. Anyways, we have normal Sudoku rules apply, which means in every cell in the grid, place a single digit such that every row, column, and designated 9-cell region contains the digits 1 through 9 exactly once each. We also need to color the grid using two colors so that each color forms a single orthogonally connected region and no 2x2 block is entirely one color. So as an example, this is known as yin-yang shading. Um, it doesn't necessarily have to be two colors. It could be like one essentially shaded and one unshaded, but you could consider the unshaded one as a color itself. But what does it mean to be orthogonally connected as a region? It means you can go from any cell in that region to any other cell in that region just by going through edges, all while staying within the region. So for example, to get from here to here, you can go along these edges here while staying within the region just to get to that cell. So this is an example of a valid yin-yang shading because any cell in the blue region can get to any other cell in the blue region just by going through edges while staying within the region. And same with the white region. The white region can be, you can go from any cell in the white region to get to any other cell in the white region just by going through edges, all while staying within the region. This would be an invalid shading because, for example, these cells here cannot no longer get to these cells just by going through edges while staying within the region. They have to go through a corner, or they would have to exit the region by going through an edge, neither of which is allowed in valid yin-yang shading. Also, this is not valid as yin-yang shading because this 2x2 area is all entirely one color, and that's not allowed in yin-yang shading. So that's an example of how yin-yang shading works. Digits in a cage sum to the total shown in the cage's top left corner. So these two digits must add up to 12. So for example, if we had a 4 here, this would have to be 8 because the digits in this cage must add up to 12 because they have a 12 in the top left corner. Okay. Within each cage, all odd digits must be one color, and all even digits the other color. This odd-even color assignment is consistent across all cages. That is, if odd digits are pink in one cage, then all odd digits in every cage are pink. So, for example, if we did have a 4-8 pair here, then these would have to be, if these were white, that means all the digits in cages that were blue would have to be odd, and all the digits in cages that were white would have to be even, if that were the case, right? And that's the color constraint for the yin-yang shading, right? Is just specifically in the cages, all odd digits are one color, and all even digits are a different color. And finally, we have digits separated by a white dot are consecutive. So, for example, well, if this were, say, a 6, this would have to be 5 or 7 to make sure that those digits are consecutive. And have fun. We will try. Those are all the rules. If you like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's learn how to Sudoku. Okay. So, on... let's start here. We know exactly what these digits are here. To add up to 6 with 3 digits, 3 unique digits, it must be 1, 2, and 3 to add up to that. There's no other combination. And this digit is consecutive with the other 2. So this must be 2, which is consecutive with 1 and 3. So these are one shading, and the other shading is these digits here. So we'll make this green, and we'll make these blue. So in yin-yang shading, you can only change colors on the edge of the grid either 0 times or 2 times. And the reason why you know that is, well, so first of all, any change of shadings has to be in even numbers, right? If you change a shading here, and then you change another shading again, and then you change another shading again, you have to be able to change back to the shading here. So even if you assume you had multiple changes of shadings along the edge of the grid, you have one swap here, you have to swap again, that's 2. You have to swap again, that's 3. You have to swap again, that's 4. You have to swap again to blue, that's 5, and then you have to swap back to the green, right? And that's just normal. Like if you swap, you always have to swap back. You can't have a change of shading then leading to no other swap, no other change, right? So you're always going to have a change of shadings on the edge of the grid of 0, 2, 4, 6, 8, whatever. Now the question is, what happens if you try to change shadings more than twice? So say we change shading to green here from the blue, somewhere. What happens? How do you get a single change of single region that is going to be orthogonally connected? Well, how do you do that? You have to connect this to the other green cells orthogonally, right? Where they can go from any edge to any other. You can go from any cell in the region just by going through edges while staying within the region. But the problem with doing this is that it breaks apart the blues into 2 separate regions. And what happens if you try to connect the blues together orthogonally? You get the same problem for the greens. The greens would be broken up into specifically only 2 separate regions when it's supposed to be a single orthogonally connected region. So that's why you cannot have more than 2 changes of color on the edge of a grid in yin-yang shading. So, if you know we have a change of shading here because this is odd, this has to be even, and this is odd. Actually, let's make it typical. I usually make the evens blue and the odds red in the puzzle. So, we know we have one change of shading here and another change of shading here. And you can only have 0 or 2 changes of shading on the edge of a grid for yin-yang shading. And this is specifically for yin-yang shading only. So therefore, we don't have any other changes of shading in the rest of the puzzle. Or, sorry, on the edge of the grid. So therefore, these must all be red. And if they are in a cage, they must be an odd digit. Well, if you ever have 2 unique digits adding up to an even sum, they must either both be odd digits or even digits. So they're basically digits of the same shading no matter what. So since this is 14, that's an even sum with 2 unique digits. They must add up to an even... Actually, just doesn't have to be unique digits, just 2 digits in general. If you ever have two digits in general trying to add up to an even sum, they must either be both odd or both even. So since this is odd, this also has to be odd here. That means, okay, so we also have the rule again where no 2 by 2 area can be the same color. So that means for this 2 by 2 area, this must be even. This must be even. Same with this. This must be blue. Or not, it doesn't have to be even. It just must be blue. And if it's in a cage, so this must be blue. This must be blue. Okay. Again, to add up to an even sum, this has one odd and one even, which adds up to an odd sum. So to add up to an even sum here, we need another odd here. And it's the same with this for this 12. So we have odd and odd there, which makes these both blue because we have a 2 by 2 area that's all red. Now, okay, so this blue area has to exit out to orthogonally connect to the rest of the blue area. Now, this is another, deduction you can make about yin-yang shading, is that if you have a diagonal that's one color, you can't, the other digits, the other cells on the other diagonal cannot be the same shade. Now, the reason why is if you try to have them both the same color as a diagonal that's the same color, then you have a 2 by 2 area that's all the same color, which is not allowed. But if you try to make it the opposite color, well, what happens if you orthogonally connect them? If you orthogonally connect them, the problem is the other diagonal is necessarily broken up into two regions, which is supposed to be a single region. And it's the same thing if you do it the other way, obviously, because it's basically symmetrical. So if you try to connect the blues orthogonally, that will break the reds on the diagonal into a multiple regions when it's supposed to be a singular region. So, because we have this diagonal that's both blue and this diagonal that's both blue, the other diagonal has to be not the same color. So since this is red, this must be blue here. And also we have to orthogonally connect anyways for this cell here. So that's going, but that's in general sort of a deadly pattern for yin-yang shading, is that you cannot have a diagonal of one color and then the other diagonal be the same shading no matter what. If it's the same color, right, because then it makes that 2 by 2 area the same color, or if it's the opposite color, you'll necessarily break the yin-yang shading because you'll have to break one of those shades into multiple regions. So this must be blue. This has to exit out and orthogonally connect to the blue region, so that's also blue. These are the same shading because they add up to an even sum. And if you tried to have them both blue, you'd have a 2 by 2 area that's all blue, which is not allowed. So these must both be red. Again, we have the diagonal here, which is the same shading. So this cannot be blue because we already have a blue there. So this must be red. Blue has to orthogonally connect to the rest of the blue areas. And in this cage, we have a 7. We already have 2 blues, which are even. Well, the only digits which add up to 7 are 1, 2, and 4. So we already have the 2 and 4 accounted for by the even digits. So this must be odd here. Blue must orthogonally connect that way. To add up to 16, we have an even sum here. And even plus even must add up to an even sum. It cannot be even and odd. That would add up to an odd sum. So this must be even also for the 16. These three, so we have a 2-4 pair here. We have all of these cells that are blue in an even in these cages. So that means this must be 6 and 8 as possibilities here. This must add up to 16, and it's all evens. So that means the rest of... So to add up to 14, the only odd digits are 5 and 9. You could have had 6 and 8, but that doesn't work otherwise. So this is 5 and 9 here. The rest of column 2 has to be 1, 3, 5, 7, 9, because we have used up all the even digits in column 2. And this has to be 1 again, because we have 1, 2, and 4 adding up to 7. 16, we have 3 even digits. So I think it has to be 2, 6, and 8. Yeah. 2, 4, 6 adds up to 12. 2, 4, 8 adds up to 14. 2, 6, 8 adds up to 16. And 4, 6, 8 adds up to 18. So this must be 2, 6, 8 as a triplet here to add up to 16. These two, we have these 3 digits adding up to 23. That's uniquely must be 6, 8, and 9. Those are the only digits that can add up to 23. This is an even digit because it's blue, and so the 6, 8, 9 eliminates 4, 8, and 3, 9 as possibilities to add up to 12, so this must be 5, 7. Well, that leaves the remaining digits in row 7 as 1, 2, 3, 4, because we have a 5, 7 pair and a 6, 8, and 9 triplet in the row. So this is 1 through 4. This can't be 1, though. This is 1 through 4, and this is 1 through 4 as possibilities. Okay, remaining digits in row... Well, in this 7 cage. Cannot be 5, so it can't be 2, 5, so it's either 1, 6, or 3, 4. But this can't be 1 because of 1 in the box, so this can't be 6. Okay, this is 6 or 8, adding up to 12. These have to be 1, 5, and 2, 4 as a pair, as those are the only possibilities that add up to 6 with 2 unique digits, and that eliminates 1, 2, 4, 5 in the rest of row 3. So this can't be 1. This is then 3, 6, 7, 8, 9, 3, 6, 7, 8, 9, 3, 6, 7, 8, 9, 3, 6, 7, 8, 9. The 3 cannot be here because 3 plus a single digit never adds up to 13, right? Because 10 would have to add up to 13. So this must be 6, 7, 8, or 9, which adds up with 4, 5, 6, and 7 to add up to 13. These digits add up to 13. It can be 1, 2, 3, 4, and 7, because this is 3, 6, 7, 8, 9. So 9 would be with 1, 8 would be with 2, 7 would be with 3, 6 would be with 4, and 3 would be with 7 here. Okay. What else do we have? Where is 7 in this left central box here? Can't be here because of the cage. Can't be here because it adds up to 7 with that cage. These are all even. This must be even, and this is a 1. So 7 has to be here, which eliminates 7 in the rest of the column. This can't be 5 because of the 5, 9 pair in the row, so this can't be 8 here. These are the same shading. These are the opposite shading, right? Because 1, 5 adds up to 6, and 2, 4 add up to 6. These are the same shading. We don't know which. So let's just mark these. These are separate, different shadings. We don't know which one this is. We're just going to mark it as the same. These have to be different shadings, and these have to be different shadings here. Okay. Hmm. This has to orthogonally connect to the rest of the blues, so we have to get blue there, which means this cannot be 9. So this is 6, 8 as a pair, which eliminates 6 and 8 in the rest of the row. So this can't be 6 or 8, it's 9, which is odd. This must orthogonally connect to the rest of the blues, as must this. So these are both blue. So this is even. To add up to 10, you can either have 1, 2, 7, 1, 3, 6, or 2, 4, 5. Sorry, 2, 3, 5. Right? 1, 2, 7, 1, 2, 7, 1, 3, 6, 1, 4, 5, or 2, 3, 5. Okay. Well, since this is even, these either must be 2 evens or 2 odd digits here. They cannot be 2 evens because we already have 3 evens in row 5, which would give us 5 evens in row 5 if they were both even. So these must both be odd. And since these are both odd, we have a 2 by 2 area that's all red. This can't be red, that's blue. And these are different shading, so this must be red there. Well, this to orthogonally connect out has to get to here. So therefore, this is blue. These are the same shading. So therefore, they must be both blue. We have a diagonal again that is the same shading. So these cannot be the same shading. That's blue anyways to orthogonally connect. This blue must orthogonally connect to... this is blue. Therefore, both of these must be blue to add up to an even sum. So this is blue here, and it's the only even pair there. So that's a 4-8 pair, because 3, 9 are odd and 5, 7 are odd. If this were even, we'd have a 2 by 2 area that's all even. So this cannot be even, therefore this must be odd, which means this can't be odd. These must be even because we have a 1, 5 and 2, 4 pair here. So this must be 1, 5, which makes this 2, 4. Okay. What else do we have? That's even, that's even. Oh, yeah. To add up to an odd sum, we have to have an odd and even pair here. Right? This is even already. So to add up to an odd sum, this must be odd. Well, to add up to an odd sum for 2 cells, one must be odd, one must be even. So this must be 2 evens and an odd here. This is even because it's in a cage and it's blue. That means the rest of the row has to all be odd. So this must be 3, 5, 7, or 9 there. And this is 2 evens. It cannot be 1, 6, 8 because of 1 in the row. So what can it be? To add up to 15. This is even here. Again, so this is 2, 4, 6. We know this has to have an 8 here. So 8 and 2 adds 8, 2 adds with 5. So this is either 8, 2, 5, adding up to 15, or 8, 4, 3, adding up to 15. 8, 6 would have to add up with 1, but we don't have 1 here. No 3 or 5 there. It's 2, 4, 8. So therefore, we are guaranteed a 2 or 4 as the other digit here, because 8 can't be anywhere else in row 6. So 8 with 2 or 8 with 4 adds up to 15. We can't have 1, 6, and 8 here because of the 1 in the row. So this is guaranteed to have 2 or 4. This is 2 or 4. That eliminates 2 or 4 in the rest of the row. So this can't be 2 or 4. It's 6, which makes this a 1, 3 pair to add up to 10. That eliminates 1 and 3 in the rest of the box. So this can't be 1 or 3. This can't be 1 or 3. 6 eliminates... what do we lose here? We have... Yeah, we eliminated... 1 and 3. So this can't be 7 or 9 there to add up. And this is an even sum. These are even sums. So this actually has to be 2, 8, or 4, 6 there. This is even, so it's 4, 6. This must be odd, which is 7, 9. So 9 eliminates 9 here because of 9 in the column. 6 eliminates 6 here, so this is 8, which makes this 6. Remaining digits in this lower central box are 4, 8, and 9. That eliminates 4, 8, 9 in the rest of the row, so no 8 here. That's 6. That means the only even digit left we have is 2, because we cannot have 4, 8, and 9 there. 6 eliminates 6 here, so that's 4, which makes that 4 and 9. 4 eliminates 4 here, so it's 2 and 8. 8 eliminates 8 here, so it's 4 and 8. Then this must be 2 left to add up to 12. So 12 minus 6 is 6. This has to be a 1, 5 pair, which eliminates 1, 5 in the rest of the row and box. So this can't be 1, this can't be 1, 5. We have 2, 3, and 4 then remaining in this lower left-hand box. That eliminates 2, 3, and 4 in the rest of the row and box, so this can't be 3. No 2, 3, 4 here. It's 1. This can't be 8 or 9. No 8 or 9 here. No 9 there because of 8 and 9 in the row. So this is 1 and 5 here. That leaves the remaining digits in row 8 as 3 and 7. So this is a 3, 7 pair, which adds up with 2 to add up to 12 here. This is 7, 8, 9 remaining in this lower left-hand box. 7 cannot be here because of one of these must be 7 here. 1 eliminates 1 here, so that's 5 and 1. We have 7, 8, 9 here, 1, 2, 3 here. This must be 4, 5, 6 left in row 9. And 4 and 6 eliminate 4 and 6 here, so that's 5. This can't be 5 because of 5 in the row, and can't be 4 because of 4 in the column. So that's 6, which makes this 4 there. Okay, remaining digits of row 5 cannot be 1, 3 or 2, 6, 8. So we are left with 4, 5, 7, and 9. Okay. No 5 or 9 here because of the 5, 9 pair in the box. Same with this. This can't be 4 because of 4 in the box. We have a 5, 7, 9 triplet in this right central box, which eliminates 5, 7, and 9 in the rest of the box. That leaves this as an 8. And we're guaranteed a 9 here. This is guaranteed to have an 8, so this cannot be 8 here. So we have a guaranteed 8 here. Okay. 8 eliminates 8 in the rest of the column, so no 8 here, no 8 here. Remaining digits of column 7 are 1, 3, 5, 7. Remaining digits of column 8 are 1, 3, and 7. And we're guaranteed a 7 here, so this cannot be a 7 in the rest of the box. So no 7 there. Okay, this adds up to 16. Possible combinations. Well, we know 8 is here. 4, 5, and 6 work, but the problem is 4, 5, and 6 would eliminate 4 here and 6 here. Therefore, both of them would have to be 2, which is obviously not allowed. So 4, 5, and 6 doesn't work. 4, 7, oh, this is 4, which means this can't be 3, 4 as a pair. That means this is 1 and 6. So 6 would have to be blue. 1 would be red. Red, again, we have a diagonal here. So this has to be red here. Therefore, this is odd. And this must sum up to an odd sum for this to be even as a whole. But this is 2 unique digits, so this must be 1 odd and 1 even. Well, we have already 3 evens accounted for in row 5, so the only even left has to be the 4, which means this can't be 4. That's 7, which makes this 3. That eliminates this from being 3 and 4, 3, 4, and 8 adding up to 15. So this must be 2, 5, and 8 here, and this then must be a 2. So we have 2, 5, and 8. That eliminates 2, 5, and 8 in the rest of the row. No 5 here, it's 7. No 5 or 7 here, it's 9, which makes this 5. 2 eliminates 2 here, so it's 4 and 2. No 2 here, no 3 here. This is 4, which makes that 3. 6 eliminates 6 here, so it's 8. No 8 here. 6 eliminates 6 here, so it's 2, which makes this 6. No more 5 or 7 left, which means this is a 4-9 pair. 4-9 adds up with 3 to add up to 16. So that's 3 there. 2 eliminates 2 here, so it's 4 and 2. 1 eliminates 1 here, so that's 3, which makes this 1. 1 eliminates 1 here, so it's 5 and 1 there. We have a 4-9 pair in... Well, we have all the digits set except for 1 in the central box, so this must be 7. And we have a 4-9 pair in column 6, which eliminates 4-9 in the rest of the column, so therefore that's 3. That eliminates 3 in the rest of the row. Okay. We have the 2x2 area that's all red, so this cannot be red. It's blue. That makes this red because of the way that this cage works. Therefore, this is the odd digit. It's 5. That makes the even digits. It's 8, so there's no 8 here. Where is 8 in row 8? Cannot be here or here. Can't be here. It must be here. Okay. This is a 2x2 area that's all red, so this cannot be red. It's blue. One of these has to be red, and the other must be blue. If we have red here, that would force blue there, and then we'd have the deadly pattern that I talked about, which is one diagonal that's all one color, and the other diagonal that's all one color. So this cannot be red here and blue here. It must be red here and blue here. So this is 4, which makes this 9. 4 eliminates 4 here, so that's 9, which makes this 4. 5 eliminates 5 here, so it's 7, which makes that 5. The blue has to orthogonally connect, so these both must be blue to orthogonally connect. And we have a 2x2 area that's all blue right now, so we have to have a red there. And this is the coloring for the yin-yang shading. Notice that to get to any cell from the blue to any other cell in the blue, you can go through just edges while staying within the region. Same with the red. Anyways, the rest of this is just normal Sudoku. 7 eliminates 7 here, so that's 3, which makes this 7. 3 eliminates 3 here, so it's 1, which makes that 3. 1 eliminates 1 here, so it's 5. 3 eliminates 3 here, so this becomes a 1-7 pair. That eliminates 1 and 7 in the rest of the box, so this can't be 7 here. This is 3 or 6. We have a 3-6 pair in row 3, which eliminates 3 and 6 in the rest of the row, so no 3 here. That's 7. 7 eliminates 7 there, so it's 9, which eliminates 9 there, so it's 5 and 9. 9 eliminates 9 here, so it's 8, which makes that 7. So this cannot be 5, 7, or 9, which leaves this as a 1, which makes that a 3. 1 eliminates 1 here, so it's 7 and 1. 3 eliminates 3 here, so it's 6 and 3. Okay, we have all the 1s. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2s, we don't have enough information on. We have all the 3s. 4, we have 8 4s. We need the last 4, which has to be there. 5, we have 8 5s. We know where the last 5 is. It has to be there. 6s. We have 8. We don't have 8 6s, but we know the 6 in column 5 can only be here. which gives us 8 sixes, so we know where the last 6 is. It has to be there. 7, we have 8 sevens. We know where the last 7 is. It's there. 8, we have 8 eights, so the last 8 is there. 9 in column 3. 9 can only be here, which gives us 8 nines, so that we know the last 9 is there, and the remaining digits are 2s. I don't know if I would consider this very easy. It's probably one of the easiest yin-yang shadings you can do, but even then, execution-wise, I still feel this is not very easy as a puzzle. You do have to know a decent amount about yin-yang shading to actually do this. Yeah, I would consider this probably easy instead of a very easy puzzle. That's just how I would classify it, though. Anyways, I hope you enjoyed this episode of Learn How to Sudoku, and I'll see you next time on Frank Puzzles. Take care.